few parts to the demo. What I want to do is do the demo, then maybe discuss it a little bit today, and the discussion will probably roll into the next discussion class, which will be like next week on Monday. Is that on? Okay. So what I have here is a diode laser. It's a nice red color. As you can see the nice red dot if I hold the paper here. And then what I have here is a mirror that I can rotate around. Basically, what I'm going to do is I'll just rotate it and let's see what the dot does. And then I'm going to replace the mirror with a piece of acrylic, basically a clear plastic type material. And we'll let it sort of shine through one face, hit off the other, and we'll see, does the beam deflect at all? How does it deflect? What happens as we rotate this thing, and so on. Because these are the kinds of questions that we want to answer in geometric optics, which is what we're starting with today. All right, so right now the light is incident at 90-degree angle with respect to the surface. We call this normal incidence. And we would actually say that the angle of incidence is 0 degrees. The reasoning for that I'll hopefully remember to explain in a minute. So if it's normally incident, what happens is the beam hits the mirror and just bounces back off. And it's actually tilted, so in this direction, the vertical, it's not quite normally incident. So it actually is deflecting downward and hitting here. Mostly this is so that it doesn't like fly across the room and shine in somebody's eyes. It is a laser after all. Not a very high power one. So what I want to do is I want to rotate this thing. And by the way, what this table has on it is a set of numbers along the top. So it's a circular table. And it has angles written basically as you go around the table. So on. From 0, which is where it is right now, to 90 degrees. And then goes back to 0. So it's like this one would say 0, this one would say 0, this says 90, and then the one over here would say 90. Okay, and so what it lets me do is I can look on here and see where the red line is, and it tells me what angle of incidence, and then I can look at the reflected thing and see what the angle of reflection is. You might bring the camera up here and sort of point it down so it actually sees in case everybody else cannot. I think if I tilt it like this, you can kind of sort of see it. I don't want to tilt it too much because stuff will fall off. But you guys can basically see a little red stripe here if you look closely. Can you guys see it from the middle area at least? Little red line. And what I'm going to do is I'm going to rotate it by some angle. What's your favorite number between, say, 0 and 45?
7. 33.
All right, we'll do 7. All right, so I have to rotate this guy by 7 degrees. What I need in order to actually do that is I need a piece of paper that shows me roughly where the laser beam is so that I can put the paper at 7. She's right here, they're about, oops, too far. This is all of optics, by the way, is you tilt something very gently and then, oops, too far, now I have to go back. Oops, too far, now I have to go back. That's what I spent all that time before class doing, too. All right, so the camera picks it up. Does it look okay there? Yeah, you can kind of see it there. Making sure it's on the camera, too, so you can see it on the video if you can't see it from where you're sitting. All right, so I'm going to tilt it again. Doing my best to not shine the laser into our interpreters' faces. All right. Much more is going to be in your face. But can we see it, those of you who are up close? Can you see where the stripe is at? I can tilt it this way okay, and it's not going in anybody's eyes. So if you cannot see it close enough to read it, and most of you probably can't, I rotated this by 7 degrees. So it's like, here's a 7-degree mark. The laser beam is coming in this way. My mirror is right here. Beam is hitting here, and it's reflecting off roughly 7 degrees right now. So in other words, it's reflecting off at the same angle that it's incident at. So what that means is if I draw a line, like a dashed line that goes through the 0-degree point, this angle and this angle are equal to each other. They're both 7 degrees. And if I rotate it by some more, now what's your favorite angle? They're not letting you pick, are they?
76.
All right, 5 it is. Rotate it to 5, gently, gently, gently. All right. So I rotated it to 5. You're not going to see much difference because you only chose a small angle difference. But now it's incident at 5. It exits also at 5. All right. Quickly.
20.
20. All right. So to get it to 20, let's go right about there. Oops. Bumped it a little. There. Now it's at 20. If I rotate it so that you can see it, actually it's going to reflect to me so you guys are safe now. Block it with my bulk. And you can see where the stripe is at. It's coming in from this side 20. So if I put my finger right at this 20, there's the beam. It's leaving, sure enough, it's leaving on the 20. Okay, so what we're seeing here is whatever angle we put in, that's the angle that it's going to leave at. Theta I and theta R, the incident and the reflected angles, are equal to each other. All right, this is what's called law of reflection, or it's part of the law of reflection. The law of reflection actually has 2 parts to it. My apologies, this chalk is a bit squeaky today. So law of reflection has 2 parts to it. Part 1 actually has to do with how the angles are all defined for this. Basically what's going on is I have a beam that's incident on the mirror or on any interface. I have a beam that's reflected from the mirror or the interface. And I have a third line which is called the normal line. That's what this dashed line represents. The dashed line is actually perpendicular to the mirror face. So we call this the incident ray, the reflected ray, and the normal line. Those 3 lines are all in the same plane. So incident, reflected, and normal. And they're all, we could call it coplanar. It's my shorthand for all in the same plane. Okay, so among other things, that means that when we're looking at this diagram that I've drawn a ray here, I've drawn a ray here, and I've drawn a line here. It means that it's not just a perspective thing. They actually, all 3 should be able to fit on the board together correctly, because the board defines a plane and all 3 have to be in the same plane. All right. The second part of the law of reflection, this is the part that most people remember, and it's the part that usually you actually make use of, is that the angle of incidence and the angle of reflection are equal to each other, where we've defined those angles as angle between the ray and the normal line. So shorthand, it's theta incident and theta reflected are equal to each other, where theta incident is angle, or theta reflected is angle between normal line and incident or reflected ray. Okay, so I've shorthanded it again by basically putting both coefficients here and just writing which one goes with which. So I goes with incident, R goes with reflected. If you're trying to think of some other word for incident, you could think of it as the incoming ray or the initial ray, the ray that is first shined from the laser to the mirror. The reflected ray is the one that's hit the mirror and bounced off. All right, so that's the law of reflection. I'm not going to do much more with it for the moment, but we will want to come back to it later. Because I want to do the other half of the demo now, so I don't have to lug all this stuff back next time. The other half of the demo means I take the mirror away. Note that the laser's off while I do this. It's a point of safety. So I take that piece away, and now I want to put this piece in place. This piece I'm going to put like this. This one I'm not going to be able to tilt as much because it turns out the mirror has a little magnet on the top that helps it to stick to the board. This one doesn't. So sorry for not being able to tilt it quite as much. I do want the camera again. And once again, I want to make sure that I don't shine this into too many people's faces. There's going to be a bit more beams to keep track of, though. In fact, there's actually going to be 2 beams at least, and possibly 3, not counting the incident one. Okay, so it goes through, it hits you. Where's the reflected beam going? The reflected beam reflects down, so we're good. All right, so right now, we're not quite, there we go. There's normal incidence. There. Right now, you can see basically, or could see if I use the paper, a few different beams. There's the incident beam. It's right here. That's the one that leaves the laser, goes through this thing. There is down here, because it's reflected downward, the reflected ray. It's actually reflected off the front surface of this thing. And then actually on Espen is the, we'd call it maybe transmitted ray, for lack of a better phrase. It's the ray that's made all the way through the piece of glass. And actually both are stretched out a bit. That has to do with the fact that this piece of glass has some shape to it. It's actually like semicircular or semi-cylindrical. So the cross-section is semicircular. What I want to do is I want to turn the table a little bit and see what happens. We already know what should happen to this reflected ray. We expect it to just turn as we turn the table because the reflected ray is acting the same as this mirror is. It just happens to be stretching out because of the shape of the new mirror. But we also want to look at the beam that's hitting Espen and see what it does as I move this thing. And in fact, what I'm going to do is I'm going to rotate the whole thing. Whoops! I'm going to rotate the whole thing to put the ray over there so you guys can see it. So you see kind of a line below the screen. can't make the screen go lower to catch it. Nothing I can do about that. What I'm going to do is I'm going to rotate this thing, and we're going to see, does that ray move when I rotate the piece of glass? Well, acrylic. Ready? Rotating. And the camera should be able to pick up a few rays on the table, so you're good holding it there. You see that the rays kind of moved along the wall a bit, though. And the camera from above can now see that rather than just having a beam hit and go straight through, there's now a beam that hits here and then kind of reflects off this way, which actually tells us what angle I rotated it by. And there's also the beam that goes over there that leaves a little trail here, which tells us something about how much that one's been rotated by. Okay. And there may actually be another somewhere beam. It's actually right here. Why is there a new beam that we didn't see before? Well, there isn't, but what's happened is now we can actually distinguish between reflections from the front surface and the back surface. So what I'm looking at here is actually the reflection from the back surface, which is what this red line represents. The one right here represents the reflection from the first surface. And then this one right here is what's been transmitted. Now, as I rotate this, we should see both of these things rotate with it. And then at some point, if I rotate it enough, make sure that this is still contained. If I rotate it enough, we notice something. What happened to the beam that was on that wall? Okay, so let's put it back on the wall. There it is on the wall. I'm going to rotate it, rotate it, rotate it, and it's going to wrap around a little bit. So I'm going to actually just move the whole thing so we don't wrap it around this way. Keep rotating. Oops, rotating in the wrong way. Keep rotating. What happened? It's gone. So there's still a beam there, but that's one of our reflected beams. We already established that that's one of the reflected beams from watching where stuff went. If I rotate just a little bit the other way, it's going to reappear on that wall. Right there. So it's not because I've rotated it off the wall. It's because it just disappears. So one question that we want to answer is, why does it just disappear? Why is it that it just vanishes? And by the way, does it always do that? The answer is no. If I turn this piece around, it will not disappear. In fact, if I put this piece like this, and I'm using a little guideline to make sure that it's got the same alignment as before, still have a ray at output. If I rotate, I can rotate as much as I want. And the ray never really disappears until I've rotated to the point where I'm no longer hitting the glass. And then you just get this one piece here. Okay. So one of our questions is, why does it disappear for one orientation and not for the other? Another is, why does rotating the piece of glass cause the beam to rotate? And if you don't believe me that it's the piece of glass, I've pulled the piece off. I'm going to turn it on again. I'm going to align it so it's there underneath the screen. And I'm just going to rotate this thing so you can see that it doesn't really move a whole lot. I've got to put this in place so I don't jostle anything. But I can rotate this, and as long as my hand doesn't block it, beam stays there. But if I put the piece of glass back in, and I rotate, it moves. So it is in fact rotating this piece of glass that causes that beam to move. There's a that gives us a sort of primary and secondary question. The primary being, why does the beam move back and forth along here when I rotate the glass? The secondary being, why does it disappear once I rotate the glass a certain amount? There's actually a tertiary question for what that's worth, which is, why is it that with the glass in place you get a line here instead of a dot? Because again, if I turn it on with the glass in place, you see a nice red line. If I take this out, it's a dot. In place, line, out, dot. So tertiary question, why does it do that? The tertiary question will likely be something that we have to answer in a future class, though. I want to at least try to get through the other two today. Okay? Would you guys, lights? And I'm going to turn this thing on so that we have our notes up to look at. Whoops. Those are the notes. There's the notes. All right. There is, by the way, a clicker quiz, but I think I'm going to skip over it because might as well, unless you guys really want one today. This, by the way, is the usual, here's what your homework would be if you are trying to do it out of the book because you've made that decision to not use WebAssign until the last 2 weeks or whatever. Apparently that's a thing in this class and whatever. Whoops. So what we are doing in the book at this point corresponds to chapters 7, part 1 and 2. So if you're reading along in the book, we're doing sections 7.1 and 7.2. And the focus of these two, no pun intended, is reflection and refraction. And towards, maybe on next Monday when we come back to regular lectures, we'll do stuff like attempting to draw free body ray diagrams, not free body diagrams, ray diagrams, and figure out where images are formed and so on. And that actually will help us answer the tertiary question. Today, all we want to look at is law of reflection, which I've already written for you on the board, and law of refraction, which is sometimes called Snell's law. It's named after a person whose name is Snell. So reflections themselves actually come in two general types. Sometimes they call it regular and irregular. I usually call it specular and diffuse. Specular is like what you see when you have a mirror and you reflect something off of a mirror and it's nice and sharp. You get a sharp image. Diffuse is what you get when you're reflecting off of some other surface. Like if I deflect something off of this wall, if I reflect light off the wall, you're getting a reflection. If you weren't, you wouldn't see the wall. But it's not a particularly focused or tight reflection. Okay, so here I have a laser reflecting off the wall. It's bright because the laser itself is very bright. Here it is reflecting off of the screen. This is mostly a diffuse reflection. In fact, you can see sort of a little halo around it and so on. A specular reflection would be more like if I had a really nice mirror that I'd put here and I shine the laser at it, in which case it's going to hit somebody in the face and it's kind of bright, so it wouldn't feel very good. Usually when we draw ray diagrams, when we're trying to find images, when we're talking about Snell's law and the law of reflection and so on, we're more or less assuming a specular reflection. But in reality, both are usually present in mixed amounts. Even for a really nice mirror, there's still going to be a little bit of diffuse reflection. And even for something like the floor, there's still a little bit of specular reflection. You can actually see it even on the floor. For example, from where I'm looking, there's like a little bright spot on the floor, which is caused by one of these overhead lamps reflecting and coming to my eye. That's more or less a bit of regular reflection, of specular reflection. But on the other hand, from where you guys are all sitting, light shouldn't be able to just straight travel from there, hit the floor, and reach your eye if it's also hitting the floor from the same spot and reaching my eye. You can still see the floor though, which implies that there's some specular reflection present. So diffuse reflection, excuse me. Diffuse reflection is basically what is responsible for our being able to see everyday objects. You have to see the light reflected off the object to see the object. Regular is what helps us to do stuff like image formation. We're going to look at ray diagrams, but I'm not going to do very much with them just yet. Basically, rays have the similar definition to what they have in a geometry class. It's like a straight line segment that tends to go in a particular direction. If you're drawing an actual ray diagram, it means the rays are showing you the general direction that light is traveling through the system. Most of the time we'll treat illumination as if it comes from a beam of light, which is a grouping of parallel rays. I already told you and shown you a little bit about what the law of reflection is. This is it in a prettier diagram than the one that I've drawn. All it says is you have an incident ray, you have a reflected ray, you have a normal line. Those three should be in the same plane as each other. Incident and reflected are going to be the same angle. The normal line, one word about that one before I move on. We talked earlier in the semester about forces, and I introduced to you the normal force. Does anybody remember the normal force from the forces chapter? I think that was chapter 3. The normal force was the force that exists between two solid objects to prevent them from passing between each other. But it got the name normal because the force always acts perpendicularly to the surface that's applying it. So normal is another mathematical name for perpendicular to. So the same kind of thing is going on here. This normal line has to be normal to the surface that it describes, means it's in a direction perpendicular to the surface. So if this table is my surface, the normal line should be either straight up out or straight down into the table. I do have a diagram that kind of sort of helps show what's going on with specular and with diffuse reflection. Basically, you have two different surfaces. This one right here is like a really nice smooth surface. Think of a lake that there's absolutely no waves on. It's nice clear water. Or think of a nice flat mirror. It doesn't even have to be flat, it can be curved, it just has to be smooth. This one right here is anything else, anything that's kind of a rougher surface. And as it turns out, on a microscopic level, most surfaces have quite a fair degree of roughness to them. So that means that in both cases, you're going to get both types of reflection, especially the diffuse reflection. And what's happening is each one of these rays in both diagrams is reflecting off of the surface, obeying this law of reflection. So any one ray that you pick is hitting and then reflecting, and if you drew a normal line at the location where it hits, you'll see that the incident and reflected angles are in fact equal at that point. But because the surface is really rough, the direction of the normal line changes, and so the direction in which the light sort of reflects off of, you might say the direction in which it scatters, is sort of random. It's actually kind of a good thing as far as being able to see stuff is concerned, because that means that if you have a rough surface like this chalkboard, even though the light may be coming from one particular location, it can reach everybody's eyes because there's enough surface roughness that it scatters all over the place. Okay, the ray diagrams we will look at later, so I'm not going to say anything more about this here. There's a slide that sort of shows you it. The basic gist is that you can use it to find where the image of an object is formed. This one being a nice flat mirror. You put a candle. The eye is sort of what's detecting the image. And what you do is you just draw 2 or 3 rays leaving from some point on the object that you want to image. You have them hit or interact with your optical element, in this case your mirror. So they hit it, they have to obey the law of reflection. So this one reflects like this one reflects like this. If you look at these 2 rays, they're actually diverging a bit as they leave from the mirror. So when the eye looks at them, it sort of looks along the rays and sees where did the 2 rays apparently converge, and that's where these dashed lines are for. Where they apparently converge, that's where the image is formed. And in this case, this was called a virtual image because they apparently form sort of inside the mirror. There's not actually some rays present. I want to talk a little bit about refraction of light, though, because it answers the other question that I posed, which is why does this thing move back and forth? So what is refraction? It just is the bending of light as it passes across an interface. That's another word for a boundary between 2 different media. Now, why does it bend? Why does light bend when it goes through interfaces? The answer is because the speed at which light propagates is not constant. It changes as the media change. So light actually, the fastest that light can propagate, that we know of in theory, is through vacuum. And I gave you guys the speed of light or any other electromagnetic radiation in vacuum last time. We use C naught is approximately 3.00 times 10 to the 8 meters per second. So that is approximately the speed of light as it passes through vacuum. All right. Any other material, light tends to slow down a little bit as it passes through the material. The reason why it does that is a little more complicated than the scope of our course. It has to do with basically interference of waves created by the oscillation of charges within the medium. So we'll leave that aside. Basically, though, it means light's going to slow down as it passes through some medium. So what are some examples of media that light could pass through? Well, air, for example. I mean, you all saw the light pass through the air from here to here. Plastic, acrylic, glass, whatever you want to call this. Water, different types of oil. Anything that's sort of transparent or optically transparent becomes a media that light can pass through. And by the way, there are things that are not optically transparent, but are transparent to other wavelengths of electromagnetic radiation. And so even something that's apparently opaque, clothing, stuff like this, etc., might be transparent to, say, X-rays or infrared or etc. So if it's transparent, it means light's going to be able to get through it, or it means some sort of electromagnetic radiation gets through it. But it gets through it more slowly than through air. And we actually can measure how quickly or slowly light passes through a material. The way that we measure, the way that we sort of quantified that speed is what's called refractive index, or sometimes index of refraction. Different people call it one way or the other. The refractive index has the following definition. I'm just going to use the letter N. Some people like to use an eta. In fact, natively I would use an eta because I came through this via plasma physics. And N is reserved for something else. But I'll use an N because it's easier to write for you guys. N is defined as the speed of light in vacuum divided by the speed of light in some material. So this one right here, vacuum, this one right here, material, speed of light, or speed of other electromagnetic radiation. All right, so the larger the value of eta, that also means the slower light will travel through a given medium. So for vacuum, by definition, the refractive index is 1. Because you'd have speed of light through vacuum divided by speed of light through your other medium, which is still vacuum. So maybe I should say medium rather than material here. All right, so by definition, refractive index of vacuum is exactly 1. For air, light actually propagates pretty quickly as well. It's more than 1, but not much more than 1. It's close enough that we can say it's 1.00 at least. So the 3 sig figs, same. For water, for acrylic, excuse me a minute. It's not quite time to go yet. You guys know I like these. For acrylic, depends on how you've doped the acrylic and how you put the chains together, the polymer chains that make it up and so on. But rough estimate, maybe 1.48, maybe plus or minus 0.02. Okay, so as a quick example, what would be the speed of light in acrylic? Okay, this may be 1.48 to 1.52. There's some range. All right. So if we want to know how fast it's going to travel through acrylic, we utilize the equation that we've got written here, which says N is C naught over C. We solve it by multiplying both sides by C, dividing both sides by N. We end up with C is C naught over N. Now we need a value of the acrylic. So what is the refractive index for acrylic? Well, I've written a range here. Let's just pick one from the middle of the range, 0.5. So this becomes 3 times 10 to the 8 meters per second. This is 1.5. Quick mental math, 3 is twice 1.5, so we end up with 2 times 10 to the 8 meters per second. So now we know a rough speed for how fast light travels through this piece of acrylic. So what does all that have to do with the bending of light as it passes through an interface? We're not going to get all the way to Snell's law today, but we can at least do that much. What it has to do with is the light basically has a pair of properties. One is that it is particular, meaning it acts like a particle. One is that it has a wave associated with it. That means that it propagates as a wavefront. Wavefronts try to stay together in some way. So what this picture shows, here's Snell's law for what it's worth, but what this picture shows is wavefronts for light. The little black lines represent the wavefront. The wavefront tries to stick together. Right when it hits the interface, as it starts passing through, this part of the wavefront has to slow down compared to this part of the wavefront. And so in order for the wavefront to stick together, it sort of rotates inside of the media. It's kind of analogous to, or kind of like if you take a lawnmower and you're out mowing the grass. You have really tall grass, and then all of a sudden you come up on a sidewalk and you're mowing at sort of a weird angle to it. So it's like you're having to push really hard to get it through the tall grass. All of a sudden, one wheel hits the sidewalk. The mower tends to rotate because you're pushing the same on both sides. It's not exactly the same as that. There's a lot of very complicated electromagnetic, you could call it like a force in electromagnetic materials. But it's sort of similar to that. It will rotate to maintain a constant wavefront. I think that's probably where we better stop for the day.